Today is the last day on Laplace Transform and the first day before we start the rest of the term, which will be spent on the study of systems. So I'd like to spend it on one more type of input function, which in general your teachers in other courses will expect you to have had some acquaintance with. So it's the kind associated with an impulse. So an input consisted of what's sometimes called a unit impulse. Now, what's an impulse? It covers actually a lot of things. It covers with a situation where you withdraw from a bank account, for example, take half your money out of a bank account one day. Also would be modeled the same way, but the simplest way to understand it the first time through is as an impulse, if you know what an impulse is. So if you have a force, a variable force acting over time, and we'll assume it's acting along a straight line so I don't have to worry about it being a vector, then its impulse, the impulse, according to physicists, the physical definition, the impulse of f of t over some time interval, let's say the time interval running from a to b, is by definition the integral from a to b of f of t dt. Actually, I'm going to do the most harmless thing this period. I'll assume the force is actually a constant force. So in that case, I wouldn't even have to bother with the integral at all. So if f of t is a constant, let's say capital F, then the impulse is, well, that integral is simply the product of the two. The impulse over that time interval is simply f times b minus a. Just the product of those two. The length of time, the force times the length of time for which it acts. Now that's what I'm going to want to calculate, want to consider in connection with our little mass system. So once again, I think this is probably the last time you'll see the little spring. Let's bid a tearful farewell to it. So there's our little mass on wheels, and let's make it an undamped mass, and it's got an equilibrium point and all the other little things that go with the picture. And when I apply an impulse, what I mean is applying a constant force to this over a definite time interval. And that's what I mean by applying an impulse over that time interval. Now, what's the picture of such a thing? Well, the force is only going to be applied. In other words, I'm going to push on the mass or pull on the mass with a constant force. So with a little electromagnet here, we'll assume it's a pile of iron filings or something inside there. So I turn on the electromagnet. It pulls with a constant force for just between time 0 and time 2 seconds, and then I stop. So that's going to change the motion of the thing. At first, it's going to start pulling it toward the thing, and then when it lets go, it'll zoom back, and there'll be a certain motion after that. So what I want to do is, question is, if I want to solve that problem of the motion of that in terms of the Laplace transform, how am I going to model this force? Well, let's draw a picture of it first. It starts here. It's 0 for t. Let's say the force is applied between 0 and time 0 to time h. And then its force is turned on, it stays constant, and then it's turned off, and those vertical lines shouldn't be there, but since in practice you cannot, it takes a tiny bit of time to turn a force on and off. It's in practice not unrealistic to suppose that there are approximately vertical lines there. They're slightly slanted, but not too much. Now, I want it to be a unit impulse. Since the impulse is the area under this curve, so this is the force axis, and this is the time axis. Since the impulse is the area under this curve, if I want that to be 1, then if this is h, the height to which in other words, the magnitude of the force must be 1 over h. in order that the area be 1, in order, in other words, that this integral be 1, the area under that curve be 1. So the unit impulse looks like that. The narrower it is here, the higher it has to be that way. The bigger the force must be if you want the end result to be a unit impulse. Okay, now let's, to solve a problem, a typical problem then would be our spring, the mass is traveling on the track. Let's suppose the spring constant is 1. So there'd be a differential equation, and the right-hand side would be this f of t. Well, let's give it its name, the name that I gave it before. Remember, I called the unit box function the thing which was 1 between 0 and h, and 0 everywhere else. The notation we used for that was u, and then it had a double subscript from the starting point and the finishing point. So u of t. So this much represents the thing if it only rose to the height 1, but if instead it rises to the height 1 over h in order to make that area 1, I have to multiply it by the factor 1 over h. Now, if you want to solve this by the Laplace transform, in other words, see what the motion of that mass is as I apply this unit impulse to it over that time interval, you have to take the Laplace transform, if that's the way we're doing it. Now, the left-hand side is just routine and would involve the initial conditions. So the whole interest is taking the Laplace transform of the right-hand side. And that's what I want to do now. So the problem is, what's the Laplace transform of this guy? Well, let's remember, however, to do everything else, you do everything by writing in terms of the unit step function. This function that we're talking about is 1 over h times what you get by first stepping up to 1. That's the unit step function, which goes up by 1 and tries to stay at 1 ever after. And then when it gets to h, it's got to step down. Well, the way you make it step down is by subtracting off the function, which is the unit step function, but where the step takes place not at time 0, but at time h. In other words, I translate the unit step function, of course, I don't think I have to draw that picture again. The unit step function looks like zing, and if you translate it to the right by h, it looks like zing, and then make it negatives to subtract it off, and what you'll get is this box function. Okay, so we want to take the Laplace transform of this thing. Well, we have to, let's assume for the sake of argument that you didn't remember. Oh, you had to use the formula at 2 a.m. this morning, and therefore you do remember it. So I don't have to write it. I don't have to recopy the formula onto the board. Maybe if there's room there, all right, let's put up there. It says that u of t minus a times f, any f, so let's call it g, so you won't confuse it with this particular one, times g translated. If you translate a function by from t, but if you translate it to the right by a, then its Laplace transform is e to the minus as times whatever the old Laplace transform was, g of s. Multiply by an exponential on the right. On the left, that corresponds to translation, except you must remember to put in that factor u for a secret reason, which I spent half of Wednesday explaining. Okay, so what do we got here? The Laplace transform of u of t, that's easy. That's simply 1 over s. The Laplace transform of this other guy we get from the formula. It's basically 1 over s, but because, no, the Laplace transform of u of t, but because it's been translated to the right by h, I have to multiply it by that factor, e to the minus h times s. So that's the answer, and if you want to solve problems, this is what you'd feed into the equation, and you calculate and calculate and calculate it. But that's not what I want to do now, because that was Wednesday, and this is Friday. You have the right to expect something new. Okay, so here's what I'm going to do new. I'm going to let h go to 0. As h goes to 0, this function gets narrower and narrower, but it also has to get higher and higher because its area has to stay 1, right? Okay, so what I'm interested in, first of all, is what happens to the Laplace transform as h goes to 0. In other words, what's the limit as h goes to 0 of, well, what is that function? 1 minus e to the negative hs divided by hs. Okay, well, it's an 1801 problem, we're under a calculus problem, but let's do it nicely. You see that the way to do it, the nice way to do it is to make a substitution. We'll change hs to u because it's occurring as a unit in both cases. So this is going to be the same as the limit as u goes to 0. Maybe u is not a, I think there are too many u's here already. Blah. I can't use u, you can't use t. V is velocity, w is weight function. There is no letter. All right, u. So it's 1 minus e to the negative u over u. So what's the answer? Well, either you know the answer, or you replace this by, say, the first couple of terms of a Taylor series. But I think most of you would use L'Hopital's rule, so let's do that. So the derivative of the top is 0 here. The derivative by the chain rule of e to the negative u is e to the negative u times minus 1, and that minus 1 cancels that minus. So it's, the derivative of the top is simply e to the negative u, and the derivative of the bottom is 1. So that limit is, as u goes to 0, that limit is 1. Interesting. So let's draw a picture this way. I'll draw it schematically. So up here is the function 1 over h times u 0h of t, our box function, except it has the height 1 over h instead of the height 1. We've just calculated that its Laplace transform is that funny thing, 1 minus e to the minus hs divided by hs. That's the top line. Nothing, all this is completely kosher. But now I'm going to let h go to 0. And the question is, what do we get now? Well, I just calculated for you that this thing approaches 1, has the limit 1. And now let's fill in the picture. What does this thing approach? Well, it approaches a function which is 0 everywhere. As h approaches 0, this green box turns into a box which is 0 everywhere except at 0, and there it's infinitely high. So keep going up there, a little up there. Now, of course, that's not a function. People call it a function, but it isn't. Mathematicians call it a generalized function, but that's not a function either. It's just a way of making you feel comfortable by talking about something which isn't really a function. It has the name, it was given a name introduced formally into mathematics by a physicist, Dirac, and he, looking ahead to the future, did what many people do who introduce something into the literature, which they, a formula or a function or something which they think is going to be important. They never name it directly after themselves, but they always use as a symbol for it the first letter of their name. I can't tell you how often that's happened. Maybe even Euler called E for that reason, although he claims it was because it was in Latin, that it's because it has to do with exponentials. Well, it's just luckily his name began with E too. Okay, so this is, that's Paul Dirac's delta function. I won't dignify it by the name function by writing that out, by putting function, the word function here too, but that it is called a delta function. So, from this point on, the entire rest of the lecture has a slight fictional element. The entire rest of the lecture is in figurative quotation marks. I'm not entirely responsible for anything I say. So this is a non-function, but you put it in there and call it a function. And you naturally want to complete, if it's a function, then it must have a Laplace transform, even though it doesn't. So the diagram is completed that way. And its Laplace transform is declared to be 1. So let's start listing the properties of this weird thing. So the delta function, its Laplace transform is 1. Now, one of the things, we haven't yet expressed the fact that it's a unit impulse. In other words, since the areas of all of these boxes, they all have areas 1 as they're shrunk this way, they get higher that way. By convention, one says that the area under the orange curve remains 1 in the limit. Now, how am I going to express that? Well, it's done by the following formula, that the integral, the total impulse of the delta function should be 1. Now, where do I integrate? Well, from any place that it's 0 to any place that it's 0 on the other side of the that vertical line. But in order to avoid controversy, people integrate all the way from negative infinity to infinity, since it doesn't hurt, does it? It's 0 practically all the time. So this is the function whose Laplace transform is 1. Its integral from minus infinity to infinity is 1. Now, what else can we calculate for it? Well, I'd like to calculate its convolution. Oh, okay. Here's f of t. Let's, f of t, what happens if I convolute it with the delta function? Well, if you go back to the definition of the convolution, it's that funny integral. You're going to do a lot of head scratching because it's not really all that clear how to integrate with the delta function. Instead of doing that, let's assume that it follows the laws of the Laplace transform. In that case, its Laplace transform would be what? Well, the whole thing of a convolution is that the Laplace transform of the convolution is the product of the two separate Laplace transforms. So that's going to be f of s times the Laplace transform of the delta function, which is 1. Now, what must this thing be? Well, there's some ambiguity as what it is for negative values of t, but if we by brute force, decide that t, for negative values of t, is going to have the value 0, that's the way we make things unique. In fact, why do we make f of t unique that way to start with? So this is a function now which is allowed to do anything it wants on the right-hand side of 0, starting at 0, but on the left-hand side of 0, it's wiped away and must be 0. Okay, this is a definite thing now. Its convolution is this, and the inverse Laplace transform is the answer, in other words, is the same thing as u of t, what f of t would be. It's the same thing, f of s. And so the conclusion is that these are equal, since they must be unique. They've been made unique by making them 0 for t negative. In other words, applied to a function, well, I won't recopy it, but the point is that delta t for the convolution operation is acting like an identity. If I multiply in the sense of convolution, it's a peculiar operation, but algebraically it has a lot of the properties of multiplication. It's commutative, it's linear in both factors. In other words, it's almost anything you would want with a multiplication. It has an identity element, identity function, and that identity function is the Dirac delta function. Okay. Anything else? Yeah, I'll throw in one more thing. I won't offer a phony. It would just require one more phony argument, which I won't bother giving you. but it's not totally implausible. After all, u of t, the unit step function, is not differentiable. It's not a differentiable function. It looks like this. Here its derivative is 0. Here its derivative is 0. And in this class, it's not even defined in between, but I don't care. I'll make it go straight up. So the question is, what's its derivative? Well, 0 here, 0 there, and infinity at 0, so it must be the delta function. It has exactly the right properties. So the same people who will tell you this will tell you that also. And in fact, when you use it to solve differential equations, it acts as if that's true. I think I'd give you an example on your homework. Let me now show you how a typical example of the way the Dirac delta function would be used to solve a problem. Let's go back to our little spring, since it's the easiest thing. You're familiar with it from a physical point of view, and it's the easiest thing to illustrate on. So we've got our spring mass system, where is it? Isn't it on the board? Yeah, up there, that one. And the differential equation we're going to solve is y double prime plus y equals, and now I'm going to assume that the spring is kicked with impulse A at time, I'm not going to kick it at time t equals 0, since that would get us into slight technical difficulties. Let's kick it at, anyway, it's more fun to kick it at a time pi over 2. So the thing is, what's happening? We got to have initial conditions. The initial conditions are going to be, let's start at time 0. We'll start it at the position 1. So I take my spring, I drag it to the position 1, I take the little mass there, and then I let it go, and so it starts going back. But right at when it gets to the equilibrium point, I give it up. Okay? With unit impulse. I started it from rest, so those will be the initial conditions. And I want to say that I kicked it with not with unit impulse, but with the impulse A, bigger. And I did that at time pi over 2. So how are we going to say that? Well, kick it means delivered that impulse over an extremely short time interval, but in such a way kicked it sufficiently hard that the total impulse was A. The way to say that is kick it with the Dirac delta function translated to the point time pi over 2. Not at 0 any longer. T minus pi over 2. But that would kick it with a unit impulse. I wanted to kick it with the impulse A, so I'll just multiply that by the constant factor A. Let's put this over here so it doesn't. Y of 0 equals 1. That's the starting values. Okay. Now we have a problem. The only thing new in solving this with the Laplace transform is I have this funny right-hand side. But it corresponds to a physical situation. Okay, let's do it. You take the Laplace transform of both sides of the equation. Remember how to do that. You have to take account of the initial conditions. So the Laplace transform of the second derivative is you multiply by s squared. And then you have to subtract. You have to use these initial conditions. This one won't give you anything. But the first one means I have to subtract 1 times s. So that's the Laplace transform of y double prime. The Laplace transform of y, of course, is just capital Y. And how about the Laplace transform of the right-hand side? Well, we'll have the constant factor A because the Laplace transform is linear. And now, to get the delta function would have the transform 1. But when I translate it pi over 2, that means I have to use that formula. Translate it by pi over 2 means take the 1 that it would have been otherwise and multiply it by e, that exponential factor. So it would be e to the minus pi over 2, that's the a, times s, times 1, which would be the g of s, the Laplace transform of the delta function before it had been translated. But I don't have to put that in because it's 1. I'm multiplying by 1. And now, do everything now is routine. solve for the Laplace transform. Well, what is it? It's y is equal to. I put the s on the other side. That makes it the right-hand side the sum of two terms. And I divide by the coefficient of y, which is s squared plus 1. So the s is over on the right-hand side, and it's divided by s squared plus 1. And the other factor is there, too, and it, too, is divided by s squared plus 1. Okay, and now we take the inverse Laplace transform of those two terms and add them up. What do we get? Well, y is equal to the inverse Laplace transform of s over s squared plus 1 is cosine t. Now, for this thing, we'll have to use our formula. If this weren't here, the inverse Laplace transform of a over s squared plus 1 would be what? Well, it would be a times the sine of t. In other words, if this is the g of s, then the function on the left would be basically a sine t. But because it's been multiplied by that exponential factor, e to the minus as, where a is pi over 2, I have the left-hand side has to be changed from a sine t to what it would be with the translated form. So the rest of it is u of t minus pi over 2, because a is pi over 2, and times what it would have been just from the factor g of s itself. In other words, a times the sine of, again, t minus pi over 2. So I'm applying that formula, but I'm applying it in that direction. I start with this, and I want to recover the left-hand side, and that's what it must look like. The a, of course, just gets dragged along it for the free ride. Now, as I emphasized to you last time, and I hope you did on your homework that you handed in, you mustn't leave it in that form. You have to make cases because people will expect you to tell them what the meaning of this is. Now, if t is less than pi over 2, this is 0, and therefore that term doesn't exist. So the first part of it is just the cosine t term if t lies between 0 and pi over 2. What if t is bigger than pi over 2, then this factor is 1. It's the unit step function, and I therefore must add in this term. Now, what's that term? What is this? What is the sine of t minus pi over 2? The sine of t looks like that. The sine of t, if I translate it, looks like this. If I translate it by pi over 2, and let's finish it up, you know, the chi that was over here moved into position. So that curve is the curve negative cosine t. And so the answer is, if t is bigger than pi over 2, it is cosine t minus a times cosine t. Or in other words, it is 1 minus a times cosine t. Now, do those match up? They've always got to match up, or you've made a mistake. You always got to get a continuous function when you have just jumped us continuities. Do we get a continuous function? Yeah. When t is pi over 2, the value here is 0. The value of this is also 0 at pi over 2. So there's no conflict in the values. The values doesn't suddenly jump. The function's continuous. It's not differentiable, but it is continuous. Well, what function does that look like? Well, there are cases. It starts out life as the function cosine t. So it gets to here. And at t equals pi over 2, the mass gets kicked, and that changes the function. Now, what are the values? Well, if a is bigger than 1, if a is bigger than 1, this is a negative number, and it therefore becomes the function negative cosine t. Now, negative cosine t looks like this, the blue guy. So negative cosine t is a function that looks like, so it goes from here, it reverses direction. The mass reverses direction from what you thought it was going to do, and it does that because A is so large that that impulse was enough to make it reverse direction. So this is what's going to happen if, of course it might only do this, but this is what will happen if A is bigger than 1. If A is, this will be A is a lot bigger than 1. If it's not so much bigger than 1, it might be, it'll only look like that. So A just bigger than 1. How's that? Well, what if A is less than 1? Well, in that case, it stays positive. If A is less than 1, this is now still a positive number, and therefore the cosine continues on its merry way. The only thing is it might be a little more sluggish, or it might be very peppy and do that. Oh dear, let's just go that far. This will be the case A less than 1. Well, of course, the most interesting case is what happens if A is exactly equal to 1. You know, the porridge is exactly just right. I think that's the phrase. Too hot, too cold, just right. It's when A is equal to 1, it's 0. It continues, starts out as cosine t. When it gets to t, it continues on ever after as the function 0. Now, I have a visual aid for the only time this term. It didn't work at all. I mean, but on the other hand, before last hour, the people who worked it were not intrinsically baseball players. So, since we'll use the equation of the pendulum instead, I don't. That's a lot easier than mass spring. So this is a pendulum. It's undamped because I declare it to be, and it swings back and forth. And here I am releasing it when, so the angle, the variable is not x or y, but theta, the angle through. So here theta is 1, let's say. That's about 1 radian, and starts there, and it swings back and forth. It's not damped, so it never loses amplitude, particularly if I swish it, if I move my hand a little bit. So I want someone who knows how to bat a baseball. That was a problem last hour. Two people. One to release it. I'll stand up and try to hold it here. Somebody releases it. And then somebody who has to be very skillful should apply the impulse, a unit impulse of exactly 1 when it gets to the equilibrium point. So who can do that? All right, who can play baseball here? Come on. Oh, okay, somebody elected? Okay. All right, come on. Okay, somebody release it too. Okay. And somebody tall to handle it all. I think that'll be me. All right, here. Okay, so just hold it at what you take to be 1 radian. And here, when it gets, he releases it. When it gets to the bottom, you'll have to get down, way down. And maybe on this side, okay, you lefty or righty? Righty. Okay, bat it with that part. Give it a good swat. Oh, I'll stand up higher. Here, wait. Help. I'm not very stable. All right. Okay. Okay, wait. Okay, we'll try a trial run. Okay. All right. Again. Okay, a little further out. Okay, first of all, you got to see where it's going to. But you stand so guys can. Why don't you stand on? Oh, you got righty. That's right. Should ask for. Okay, let's try it again. That will a little bit up more that way. Okay. Strike 1. All right, it's okay. It's the beginning of the baseball season. One more. The Red Sox are having trouble too. Okay. All right. Hey! Okay, not bad. See? Good, okay. If he'd hit it harder, if he'd hit it even harder, it would have reversed direction and gone that way. If he hadn't hit it quite as hard, it would have continued on, but more, with less, still at cosine t, but with less amplitude. But if you hit it exactly right, it's fun to try to do. Tubry in our department is a master at this, but he's been practicing for years. You know, he can take a little mallet and go, boop, and it stops absolutely dead. It's unbelievable. It's unbelievable. I should have had him give the lecture. Okay, well, okay, now I would like to do something truly serious. Here, I guess. Because there's a certain amount of engineering lingo you have to learn. It's used by almost everybody, not architects and biologists probably quite yet, but it's anybody uses the Laplace transform will use these words in connection with it. So I really think it's, since it's such a widespread technique, that these are things you should know. Anyway, it'll be easy. It's just the enrichment of your vocabulary. It's always fun to learn new vocabulary words. So let's just consider a general second-order equation. By the way, all this applies to higher-order equations, too. It applies to systems. The same words are used, but let's use something that you know. So here is a system. It could be a spring mass dashpot system. It could be an RLC circuit, or that pendulum, a damped pendulum. Anything which produces this differential is modeled by that differential equation with constant coefficients, second order. This is the input. The input can be any kind of a function, exponential function, sine, cosine, could be a Dirac delta function, could be a sum of these things, could be a Fourier series, anything. The sort of stuff we've been talking about throughout the last few weeks. And let's have simple initial conditions so that doesn't louse things up. The simplest possible ones. So the spring starts at the mass starts at the equilibrium point from rest. Of course, it doesn't stay that way because there's an input which is asking it to move along. Okay, now all I want to do is solve this in general with a Laplace transform. Okay, if I do it in general, that's always easier than doing it in particular since you don't ever have to do any calculations. All right, it is s squared y. There are no other terms here because the initial conditions are 0. This part will be a times sy. Again, no other terms because the initial conditions are 0. Plus b times y, and all that is equal to whatever the Laplace transform is of the right-hand side. So it's f of s. Next step. This is an easy problem. Y, you solve for y. Well, y is f of s times 1 over s squared plus as plus b. Now, what is that? The next step now is to figure out what the answer of the problem is. What's the y of t? Well, you do that by taking the inverse Laplace transform, but because these are general functions, I don't have to write down any specific answer. The only thing is to use the convolution, because this is the product of two functions of s. The inverse transform will be the convolution of their respective things. So the answer is going to be the convolution of f of t, the input function, in other words, convoluted with the inverse Laplace transform of that thing. Now, we got to have a name for that, and those are we have to have a name for that, and that's the two words I want to introduce you to, because they're used everywhere. The function on the right-hand side, this function, 1 over s squared plus as plus b, notice it only depends upon the left-hand side of the differential equation, upon the damping constant the spring constant if you're thinking of a mass spring dashpot system. So this depends only on the system, not on what input is going into it. And it is called the transfer function, and it's usually called capital W of S. Sometimes it's capital H of S. There are different things. But let's call it, but it's always called the transfer function. What we're interested in putting here is its inverse Laplace transform. Well, I'll call that W of t to go with the capital W of S by the usual notation. So its inverse Laplace transform, well, I can't calculate that. I'll just give it a name, W of t. And that's called the weight function for the system. The weight function of the system. This is the transfer function of the system, so put in of the system if you're taking notes. And so the answer is that it's always, the solution is the convolution to this differential equation that we've been solving since the beginning of the last 3 or 4 weeks. It's the convolution of that, and therefore the solution is expressed as a definite integral of the function, the input on the right-hand side, what's forcing the equation, times this magic function, but translated by t, flipped and translated by t. So t, d, that says du for you guys over there. In other words, the solution to the differential equation is presented as a definite integral. Marvelous. Marvelous. And the only thing is the definite integral involves this funny function w of t. So to understand why that's the solution, you have to understand what w of t is. Well, formally, of course, it's that. But what does it really mean? So the problem is, what's w of t? What's w of t really? You know, not just formally, but what does it really mean? I mean, is it real? Okay. I think the simplest way of thinking of it, once you know about the delta function, is just to think of this differential equation, y double prime plus ay prime plus b, except use as the input the Dirac delta function. In other words, we're kicking the mass. The mass starts at rest. So the initial conditions are going to be what they were before. Y of 0 and y prime of 0, both 0. The mass starts at rest from the equilibrium position, and it's kicked in the positive direction, I guess that's this way, with unit impulse at time 0 with unit impulse. In other words, kick it just hard enough. So you impart a unit impulse. Okay, what's then, so that situation is modeled by this differential equation. The kick at time 0 is modeled by this input, the Dirac delta function. And now what happens if I solve it? Well, you see, everything in the solution is the same. The right-hand side, except the left stays the same. On the right-hand side, I should have not f of s here. I should have, since this is the delta function, I should have 1. So what I get is, on the left-hand side, s squared y plus asy plus by equals, for the Laplace transform of the right-hand side, is simply 1. And therefore, y is what? Y is 1 over, it's just exactly the weight, the transfer function, and therefore, its inverse Laplace transform is that weight function. That's the simplest interpretation I know of what this magic weight function is, which gives the solution to all the differential equations, no matter what the input is. The weight function is the response of the system at rest to a kick, a sharp kick at time 0 with unit impulse. And read the notes, because they will explain to you why this can be thought of as the superposition of a lot of sharp kicks. Time 0, a little later, kick, 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 kick. And that's what makes the solution. Okay, next time we start systems.